Okay, now let's look at the main computations we want to do with the Markov process. Now recall, for the Markov process we are studying, two things completely characterize the process. The first one we were saying is that the surgeon time obeys exponential distribution. What it means is that Tn plus 1 minus Tn less than or equal to t, given that the state at Tn is I, is 1 minus e to the negative lambda it. Naturally, this lambda I now is called the surgeon rate. So this is one. It describes how much time the process will stay in state I before the next jump. The second part is about where it's going to jump to, and we use a Markov chain to describe it. We call it embedded Markov chain, and we look at the state at these jump times and look at what's going to be the next possible state. Based on these two, we can do some kind of calculation. Mostly we are interested in the long run behavior of the process. So we want to find out the long run behavior. Now, how do we describe long run behavior? Usually we use this probability. The probability, say we have time t is very long, right? So we are asking, look at the process. What is the probability that your process is in state J if we know that initially the state is I? Now we know this is going to be I independent if t is very large. So we are really looking at what's going to be this probability. So long-term probability, we can say, when t is going to infinity. In general, this limit may not exist, but in certain cases it does. And that's, if you recall, the case when we have irreducible set of states. So we are going to assume that all states are in one irreducible set. So you're going to assume that all states are in one irreducible set. One irreducible set. When you look at the Markov matrix over there, excuse me. And then we can find this limit, and we call this limit Pj. So Pj describes how likely the system is going to be in state J over a long run, for a long time. Now, how can we find this Pj? Remember, in the Markov chain case, we already know how to find the long run behavior. For Markov chain, we had it this way to find it. For Markov chain, we had to solve pi is equal to pi p, right? And then we get pi. But for the Markov process, it's easy to understand. This pi does not capture all the information that we need about the process being in state J. The reason is this pi tells us only how likely this state is going to jump from I to J. But how long this system is going to stay in state J, we need to know this surgeon time distribution. So we somehow need to combine this pi, which is solved from the Markov matrix, and this surgeon rate lambda I. And how do we do that? There is the easy way to do. So let's try to somehow see the following argument. Pi over here is how likely we're going to actually end up with J if we start from I. And then after you get to J, then we need to know how long on average is going to stay in this J. So we need to know somehow what is expected value of Tn plus 1 minus Tn. And that way we can find out, and that's going to be exactly 1 over lambda. Of course, if you start from I, that's going to be lambda I, because this is how long it's going to be stay in state I. So if you want to know how long it's going to be stay in state J, so we need to actually look at 1 over lambda J. So this is how likely to get to J, and this one over here is how long it's going to stay in J. So then if you multiply them up, so pi times 1 over lambda J, this will give us how long over long run, how long this system y of t is in state J. And that's the one we have. But there is still a somehow a shortcoming of this number over here, because if you look at this number, it's no longer a probability vector. So pi j times 1 lambda j, this one over here. If you look at all of them, so look at over here, this is not a probability vector anymore. So what we need to do is to normalize it, make it a probability, and that way we have exactly what we want. So Pj, this number is in long run how much the system is going to stay in state J is the following. You normalize it, that means you put it over here, this one, put it on top, and then you divide by the sum of it, that's pi 1, and divided by lambda 1, and keep going until pi n divided by lambda n. Here n is the total number of states, so we have over here n over here is the total number of states. That way we find the long run probability vector for the Markov process. Let's go back, try to see this process, how we find it. First, we can solve pi from this equation we know how to solve, and then for each component we multiply the factor 1 over lambda j, because that's the expected surgeon time. That's what it is. But on the other hand, we can also solve this Pj, this vector, directly. We can also solve, this is just an alternative way, solve Pj directly from another system. The system is called Pg is equal to 0, and G over here is called the generator matrix. Generator matrix. We can easily see where this generator matrix is from, because we know pi is the solution. Pi is the solution of this equation. Pi 1 minus p is equal to 0, right? So if you look at this one over here, it's easy to understand that pi over pi j over lambda j, this vector, this probability vector over here, not yet a probability vector, let's say this vector over here, is a solution to the following system, is a solution to this system, to Pg is equal to 0. And this G over here is the following matrix. If you look at its entries, on the diagonal, it's exactly lambda I negative. So if I is equal to j. If it's not on the diagonal, you will see this is going to be lambda I multiplied by Pij. Now, this equation over here is completely equivalent to the older one. It's just a different form, but it will allow us to find this P factor directly. So what we can do is that we can actually form this generator matrix G from the given conditions from Pij and lambda I. And then we can solve Pg is equal to 0. But remember, if you want to use the row reduction, you need to solve really the transpose equal to 0. So that's important because P over here is a row vector again. Then after you solve it, then normalize the and solve it, and also you need to make sure that P has non-negative, has positive, let's say, positive entries, and then normalize. Normalize means you just divide it by the sum of the entries. Okay, so then we have the P vector that we need. Now, once we have this Pj, this vector over here, what can we do? We can find the expected profit over long run, the profit rate, because the time is infinite. If you add them up, it's going to be infinity. So we can only find profit per unit. And how do we do that? So we say profit per unit time is going to be expected value. So this is going to be Pj and Fj, and sigma. J is in the state space. So that's going to be the profit per unit time. Now what is this Fj over here? Fj over here is a profit rate. It's a profit rate when the process, or when the system is in state J. So it's still the similar kind of situation. So when it's in state J, we have this profit. And then we say how likely the system is going to in state J. It's Pj. So we take the probability average of this profit, and that's the one we have. Now for the Markov process that we are studying now, there is another interesting thing we can add, that we can take away the jump cost. Imagine that whenever your system jumps from one place to the other, one state I to j, you have a jump cost called hij. Now when we say jump cost, we say it's negative profit, but you can also have a jump profit, then it's positive. In the textbook, they actually have positive jump profit. But here is the way. If you consider the jump cost, then the total profit per unit time is the following. Then you will have profit per unit time. You need to first calculate this profit over here, J over here, let's say, and Pj and Fj. And then you need to take away something. Take away, but still going to be weighted by the probability. And here we have Pj. Okay, and here you need to multiply something else. This part is going to be another sum. And for each j, you need to multiply the row of the generator matrix. So this is going to be g, jk, and by the jump cost, h, j, k. And j over here, a k over here is inside e. Of course, k cannot be j because we assume that hjj is going to be 0. You have that part. Now, if you look at what we have inside over here, it's easy to understand, even though we cannot really prove it. If you think about what gjk times hjk is, this is simply lambda j and pjk and times hjk. So we can see still this is about cost. The jump cost is jk, hjk, and pjk gives us the probability jumps from j to k, And lambda j tells us the rate to get the rate the system stay in j. So this is the part that we have inside this sum over there. So if we calculate this whole thing, then we have the profit per unit time considering the jump cost.